Hey folks, welcome to the stream. Make sure my camera is adjusted properly here. So yesterday I was at a soccer match, so I could not stream at my normal time, but here we are. And because it's a holiday today in the United States, so I have the day off. I figured we can do some Gleam, some Essentials of Compilation. Where we left it last time, I think is important to call out. We had gotten kind of stuck. There was an issue with running out of stack space. And I think I know what the problem was. So we're going to try to fix that today. And if that works, it should take just a few minutes to fix it because it was a very... It's a thing that you don't encounter that often. But I think that in this particular case, I understand why. So, it took me a while after the last stream to kind of think about it and figure it out. But I think that if I show it to you, you'll see it immediately. So we should get started on that. All right, so for context, we are trying to implement functions in our language, our typed racket-like language. And we're following the book Essentials of Compilation, which I have up here in a PDF, and you'll see in just a moment. Okay, so we are going to quickly get into it. So I want to review... we had, I was digging through the source of Nibble, which is the parsing library that we use. And let's see, yeah, I don't have this running, so let's get it running. And here we go. So there's nothing technically wrong with our code. But what we hit was a case where, so if we go to parse, it doesn't output anything, but if we look in the dev tools in the console, we can see maximum call stack size is exceeded. Now what I notice about this is it says expression, nested expression, apply expression, nested. Oh, okay, so we're kind of taking this branch where we are constantly calling the same functions over and over without a termination condition. Now, it is taking other branches. It's like, hey, primitive void open, and it's like at that point, you've gotten so deep in the stack that you've got too much. So what can we do? Well, if we look at our parser, and let's look at those functions that are involved. So there's expression, which is in the stack, right? And it's one of integer, boolean, or variable, or a nested expression, something with parentheses around it. These don't require parentheses in Racket, so we don't consider those. But parenthesized stuff includes all of the complicated expressions. So like if let primitive, so this is this function, that's one of the things in the stack. If let primitive, you can see we went into primitive and went void, right? And there's begin, while, set, and then apply expression. This is the last one. Okay, now what are we doing here? We call do expression. So what's happening, I believe, is that because this is the first thing called, so like we have to call expression before we can call do, and then the rest of this is in a callback. So if we undid the use expression here, we would get do expression function with an argument of f. And inside that would be do nibble many expression, and then a callback function with args, right? So this is the essence of the problem. That's what I believe. So let's go and look at, yeah, this is fine. Let's find lazy. So what this does is takes a function with no arguments that returns a parser and wraps it. So defer the creation of parser until it is needed. Okay, it says is not a function. So the problem here is I'm just going to do lazy. I'm going to change this like so. That still compiles. And what this is doing is it is breaking the cycle. So it's saying we can just return, you know, this function without evaluating it. Right? So you won't, like, what this is doing is it's putting into a parser struct the contents of our parser function, and it defers running it until this parser is invoked, rather than you know, expecting this, which does return a parser, to return immediately and then be passed to do. So I think that this is going to break the cycle, and we should be able to find out. So let's switch over to our thing here. Okay, so we hot reloaded. Let's compile 5. We need to go back up to tokenize. Okay, so that works. Parse, do you work? Okay, so we got 5. Now, notice this parse pass is pretty printing the original expression, right? So we could go to type check, and that's probably as far as we can go. So I think we broke the cycle here. Let's do a let x 0 plus x 42. And we will go to tokenize. That's fine. Parse should give us back the same expression. So we've broken the cycle there. That is excellent. We can move on. I think that we were looking at shrink. So shrink. This is one thing that we did last time. So we instead of we had multiple, we changed our pattern here to have multiple implementations or multiple variants of our program type. This could come back to bite us. But what the main thing that shrink was doing, aside from what it has done traditionally, which is to convert the and or expressions into ifs, it was also charged with, in this chapter, converting the main body of the program into a function main. So if I think we can run shrink. Yeah, so here it's changed. This is what I wanted to show previously. It has changed our body into a function main, which returns an integer and contains that expression. So we have pretty good validation that that is correct. I think that we can now probably convert. We can go back and fix our tests for shrink, and then we can start doing the other passes. So before we do that, no, this is what we were doing last time. You can see basically we mirrored that, but we made it a different variant of the same struct rather than a different struct. I think that's, or a different type. I think that's going to have some potential to be a pain. But what we can do in our later passes is do let assert, program defs. And the thing is, we're going to convert it pretty quickly into another type of language. So we should just be prepared to do that. Okay, so let's fix up the tests for this. I'm going to uncomment all the tests, and then we are going to let's save so we get formatted. Okay, so we want to do fun. Okay, so all the places where we say program, here we want to do program. We want to have program defs and program defs expression, because those are the different things that are, or those are the two different variants. We want to start with program defs expression and just have an empty list of defs on most of these. And then we're going to say program defs. And this is going to we're going to need to bring in definition. So this is going to be definition main empty arguments, and that's the expression. Oh, integer t. Okay, and then we can do the same down here. This is going to be a little bit mechanical. The nice thing about this is that as we do this, what we're going to get is coverage for not just the stuff that we covered before, but you know, we are also getting coverage for this particular transformation. We will need to make sorry, this needs to be in a list. We will need to make adjustments for making sure that the bodies of functions also get the shrinking applied to them. And remember, this shrinking is not making fewer constructs. This is removing a particular kind of operator and turning it into pure ifs. So we're taking the and or inside expressions and turning them into ifs. And that has, I'm trying to recall exactly why we do that, but if I recall correctly, it has to do with the fact that you can optimize away certain things, or you can turn it into particular kinds of jumps in x86. So let's just continue this transformation. Okay. We're going to have to make sure that our interpret can handle these additional forms. And I'm literally just changing this to have, you know, no definitions but the body. In fact, I'm just going to copy this bit because I think that we're going to just paste it in a bunch of places. Okay, now I'm pretty certain that these tests are going to fail, but let us try them. Okay, so what we get is pattern match failed. So we're going to have to go up in here, and this hopefully should be a straightforward thing, but in our interpret, we need to handle this in our interpret and our type check. So rather than a let assert, let's go case P, and we're going to say def's body is this. I'm sorry, I need to put the pound there. Okay, def's body. Okay, and then for the other case, what we need to do is let's look at the standard library. I don't know why it showed me that. Let's look at 102, which is the latest. Okay, so we're going to take, or we're going to find, let's do find map. Find map in defs. Okay, and so this is going to take a definition. You know, the other thing that we could do is just call the main function. So let's do defs, and the body is going to be apply yeah, then we can get around that. That's a pretty nice way to get around it. So that should, okay. So now we've got line 311. We've got a problem with that. Okay, so this is the type checking. Okay, so we've got a parse problem we're going to need to resolve. And we've got we need to deal with this. So I think that what we'll do is basically the same thing as what we did in interpret, but I kind of don't want to change the semantics. What the part that I was struggling with too was and maybe I shouldn't struggle with it. Let's comment that out. We're going to say case P and add missing patterns. Okay, so for this, what we need is let def's body is that. We'll do the same thing we did above. Def's body. Okay, and then here, maybe what we do The thing is, we will do the type check before shrink. This is just for the sake of our tests. So maybe I will pull this out. Yeah, let's just do that. If we run into issues, we can address them later. So we should just be down to one failure if that works. Okay, so now we've got a failure here. Let's look at the parse test. Line 223. Okay. So how can we interpret this? We've got multiple errors. So the span is 1, 1, 1, 2. Expected integer and got lparen. So I'm assuming that's this. Expected Boolean. Expected identifier. So this is just its backtracking. Expected type name 119, 120. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19. Okay. So we have a little, I think we have a little bug here with function types. Let's look at that real quick. Okay, so if we get let's find a type. So scalar type or vector type or function type. Function type has the parens. So it's saying okay, and then on 20 to 27, expected type name vector type or type name integer. Oh, okay. Okay, so we've got that same parenthesis problem that we had with expressions going on here. So both the function type and the vector type start with parens. This is the issue. So what we need to do is pull that out. And I think I will say parenthesized, and then we'll say nibble one of. This is the cheat way. I don't know that it's going to work. Let's just do it like that. Okay. and then we will get rid of the parens here and just rely on the fact that so then what happens is the parenthesis succeeds, but you're able to backtrack within here, right? So let's see if that fixes it, or if we run in. Nah. Yeah, we ran into an infinite loop there. We need to do the lazy thing again here. Because this can... Let's do that and see if that happens. Yeah, now it works. Okay. Cool. Let's make sure that we can take our example from our test and parse it in our thingy here. Why are you not letting me paste? There we go. So we're gonna go to, first let's go to tokenize. Okay, yeah, expect that. Parse, it's fine. So it's formatting this kind of funky. I don't care that much for the way that it formatted that. Let's go to type check. And it's putting types on things. Let's go to shrink. Okay, so we've got main, we've got map, we've got ink. Looks good. Okay. Cool. So I think that we've resolved all that. I have not made a commit in a really long time, so let's go ahead and do that. Just stage all, and I'm going to say this is up to chapter 2, shrink L fun. Okay. Good stuff. Yeah, I'm not real happy with how that has formatted, but it's okay. Okay, let us go back. So now we're in the book. Okay, so we finished the shrink pass. We might, I mentioned we might, now that we've got this stuff fixed, we might want to make sure that things inside functions get shrunk. So let us make a test. Shrink inside functions test. Right, okay, so we're gonna take something like this. Let's just write a function. So we'll say define yes, takes no arguments, returns a Boolean. And this is, let's say, let's call it yes, and it takes a, which is a Boolean. And we're going to say or. Let's put a line return in there so we can see this, or a true. Okay, so this is dumb, but what we're trying to see here is that it converts that OR into inside this function into an if, right? Okay, so let's do 0, 42, because they do all that all the time. 42 all the time. Okay, so we're going to say parse.parse. Let's do let assert, okay, token tokes equals parse.tokens. And I'm going to unpipe that. Okay, and then we're going to say let assert, okay. Program is parse.parse of tokens. Okay, and then we're going to say P. We're going to say let assert program defs shrink P. And then what we're going to look for is a definition of yes. Okay. Let's just say what we want to do is see, like, extract the body expression of this function. So an example up here. Not type checking. Right, so we do this OR, and it'll be to return into if of the first one, then true, and then the second one. So, okay, so we expect the expression to be if var a, right? Bool true, bool true. That's what we expect the expression to be. And we'll do list find map. Find map over defs. And actually, find map needs to return, this is okay. Error, no. Okay. This is what I should have done earlier with the finding main. Yes, this is a Racket compiler. Hey, welcome to the stream. Sorry, I just saw your message. So we are working through this book called Essentials of Compilation, and this is a Racket, and we are compiling to x86-64. We are using the Gleam language rather than Racket to implement it, so we do have to do some translating, but at this point I'm very comfortable with the translation. I just have to do some adaptation in some places where the semantics are different. The big one being no mutable variables is the big one. So and try to write an R7RS scheme interpreter in Rust. Oh, that's very ambitious. And I think you should do that because that should be really fun. Yeah. Mutable variables are a pain. I agree. But on the flip side, when you're trying to look at, well, what do they mean by this thing, and translate it to immutable, it can kind of get tricky. I think the best, your friend on the Rust side is going to be use immutable references wherever you can, so you don't copy or clone things, and then, yeah, be very careful about what you mutate. But you should have a good time, and make sure to box any things that are recursive. Cool. Basically in Gleam everything's boxed because it has different semantics. Okay, so I think this is good. Let's run the test and see if that passed. It did not pass. So it didn't find. Oh wait, I need to make sure I use the right function name. I'm looking for the function name is yes, not a. Okay, so that passed. So basically, we're just confirming that the transformations applied by the shrink phase on or and are applied inside functions as well. So I think we're good on that. And I'm just going to amend that commit. Okay, so now let's look at reveal functions. So this is a new pass that we haven't had before. So we're gonna let's make. Oh, that's the test. So if you're working on your scheme compiler, you might appreciate or your scheme interpreter, I guess. You might appreciate the technique done here, which is lots of little passes. And the addition of lots of little passes means lots of little variations on the same language. And there are a few of them that are kind of big, I would say, and that's that they have a huge change in semantics. But I think that comes down to how do you want to directly interpret the expressions you're getting from your scheme interpreter, or do you want to transform it into like intermediate form that's easier to interpret? And that's up to you. So good luck on that. Okay, so let's read this paragraph and then we'll get started. Okay, the syntax of lfun is inconvenient for parsers of compilation and it conflates the use of function names and local variables. Right. So where you are, if you look here at our apply expression, let's see, where are we? No, wrong one. Okay. So if we're looking up here in our expression type, we have this apply. The function name is an expression, so you can say figure out what the function you're going to call is later. We were just using the var expression, but that conflates a local variable with a function name, which could mean that those two things conflict, right? What do I mean passes? Like iterate, parse the AST multiple times? Right, yeah, so you could break it, so you would have typically a reader that just gives you tokens, and then you have the parsing step, which would build up your AST. Obviously you have to do the macro handling, quasi quoting. You might be able to do that in your parsing step, but you might also need to take another step on it. But I'm talking about things like semantics preserving transformations. You might be able to take certain constructs in Scheme and convert them to simpler constructs that are easier to interpret or more efficient. That's just an idea. I have not validated that assumption, but that's kind of the theme of this book is do small transformations that preserve semantics to achieve something that's easier to compile, but you might be able to do the same with interpreting. Yep. Okay. So, syntax of lfun is inconvenient for purposes of compilation that conflates the use of function names and local variables. There's a problem because we need to compile the use of a function name differently from the use of a local variable. In particular, we use this LEAQ to load the address of the function name. Thus, we create a new pass that changes function references from varf to funref fn, where n is the arity of the function. So, okay, so this would help with our, like when we're lowering into x86 and we convert it to call q, we need to know what the arity of the function is. So, and that has to do with generating, well, so first of all, knowing which registers to put the arguments in, but also, how much you need to push the stack, etc. Okay, this pass is named reveal functions, which we just created that. And the output language is lfunref. So we're going to have to look for, I guess this is just we add this funref type to expressions. Okay, placing this pass after uniqueify will make sure that there are no local variables and functions that share the same name. The reveal functions pass should come before the remove complex operands pass because function references should be categorized as complex expressions, right? Okay, so, yeah. Okay, so basically that's telling me a couple things. If we look at the bit where we've wrapped all this up, so uniqueify comes after shrink. So obviously before explicate control. You see, we uniqueify, we do expose allocations, uncover get, remove complex operands. So I think that what they're saying is put it right before remove complex operands. That implicitly is after uniqueify. But I think I'm going to have to jump to the end of the chapter and see their, their typical graph. Assuming it's here. Yeah. Okay, so no, they're saying right after uniqueify. The thing is we may be... Okay, so uncover get. Right, so we need reveal functions and then limit functions after uniqueify. Okay, so those are coming up. Let us go. Oh, I went too far. Apologies, folks. Okay. We got through calling conventions, tail calls, yada yada. Okay. So we're going to do this right after uniqueify. So let's get uniqueify fixed. Right. Okay, so we're going to do L. One of the things about this book is they kind of don't talk about what do you need to change all the time. Except that uniqueify will always... Let's look at what it does. Okay, so it only applies it on lets. It only applies the uniqueification on lets. This get var from the env. There's Yeah, there's going to be a problem here in that we need to seed Okay, so we need to do multiple things. We need to seed the environment with the names of the functions. Um, hmm. Okay, let's start off by breaking all the things. Okay, so we're going to do elfun. This does not necessarily have a body directly. Again, we're going to have to deal with additional expressions. But what we might be able to do all right, we're going to do let assert okay, we're going to start with that. And then we want to, this is not going to change which form we have. So we want to okay, so this is string to string. So I think that we want to do is go through, we're going to build this up. So let's do list defs, list map, name, right? So we're just going to make all the functions dict from list. Okay, so then we have the names of the functions, right? What do you mean it's never used? Oh. Okay. L.program defs. There we go. Okay, so then we're going to go and we're going to update the definitions. So we're going to map over the definitions. And then we're going to say what is the field name? Uniqueify expression d.body env. Okay, so we're gonna actually have to do fold. We don't care what the counter is. We're getting rid of this. So what I'm trying to do here, just to explain, so we're going to have, this is accumulator d. And we're going to let def's counter is accumulator. Okay, and then we're going to do let's do fold right. That'll preserve the order of the definitions. Can you mutate variables in Gleam, or does it use shadowing? It uses shadowing. So it has a SSA pass basically where similar to Elixir's SSA pass, where you never really mutate it, but if you name it again, then you've basically given up your ability to access the previous one in future expressions. So we're gonna say let's do this. Body counter is this. And I'm just going to use .1. Okay, and then we're going to return 0 and counter. Okay, so now let's do defs. So what we've done here is we've transformed this from taking a program that is a single expression into a program that is a series of definitions, and we've seeded the names of the functions into the environment. So what that will mean is that if there's a let here with a variable name, we will and that variable name shadows a function name, we will add a dot to it with a number, a trailing number, and then map it into that. So like if you do a let, you're going to shadow the top level function. I think that's what the semantics of this will be. So let's handle the other types of expressions, which is really just okay. So we will do we're just recursing here basically. And this is going to be function counter 1, and then we'll do I think that we did this in begin. Yeah, let's just copy that. Oops, I got that backwards. Why did I do map fold there instead of just making it a line? Okay. Yeah, okay. Okay, and then we'll do apply. And we need to return that with counter 2. Okay. Okay, so we recurse into the function expression part of the apply and call uniqueify with the environment, and then we recurse into arguments and do the same for each of them. Yeah, I guess it doesn't really matter which order. I just felt like fold right is nice here. We could do plain fold. It's just going to reverse the output. So map fold expects. Oh, right, it takes it as separate over this from that. Okay, so it expects you to return the tuple of the accumulator and the item. I guess this is common enough. It like makes sense to me. Okay, but remember, like we only introduce unique variables in let, the let expression, so we don't need to worry about, you know, all these other things are just, you know, uniqueify the sub-expressions. I'm interested to see what this does. So let's go back here. What did I do? Shrink, uniqueify. Oh, I need to import it. What's wrong here? Okay, so we've got P. We pass it to shrink. Oh, I just need to get rid of that. Sorry, it had it like we have this sitting in here. Okay. Yeah, refresh. What are we getting? Oh, okay, forget that. We don't care. All right, so let's take our example from that test that we were looking at. Let's take this. Let's see. This does not have any. You know, the other thing that's interesting here is that we need to, on each of those functions, we need to introduce variables into the environment for all of their arguments, right? There's a question in my mind whether we need to generate, like we need to uniqueify those. I think maybe we should. At the very least, we should extend the environment with the argument names. How do you handle the inner and outer scoped environments? Well, it's immutable. So when I extend it, so I generated the first one here, which just has the function names in it. When I extend it, then I'm creating a new one. essentially. So it's like a copy. I hope that, because the environment here is just a dictionary from original string to new string. So I hope that helps understand. Yeah, let's we're going to do this. Murph will write over the arguments. And our contents is going to be a new dictionary, or rather it's going to be env. And it's going to be the counter here. And then we will, for that, this is the accumulator. I'm reusing that variable a lot. And this is the argument. Okay. So what we want to do is we want to generate a name like we did before. So we will say let counter is +1. We want to dict insert into accumulator.0. That's the environment. Arg0, because that's a string. We don't care about the type. And let's say arg0 plus, or not plus, concatenate int to string the bumped counter. Okay, name, and then the bumped counter. Okay, so we're generating a unique name for every argument as well. And then that will be in this environment so that when it looks up the unreferenced one, or the ununiqueified one, it'll find it inside the body of the function. And again, we don't need to fold right. We could have done map fold. Doesn't really matter to me. Okay. Actually, we don't want to map fold. Oh, but we do because we need to rename the arguments in the definition. All right, let's change this to map fold. And then the question in my mind is, does map fold preserve the order? So let's find out. I think it does. Yeah, it preserves the order, so we should be fine there. And it returns them right. So it returns them as the okay, so we'll so that means we need to do, since this is a list of a string to type, okay. Yikes. Um, I think I want to change this rather than fold right. I want to change it to map fold as well. That'll make things a little bit simpler. I don't have to worry about the correct order. It is handled for me. So really that's just, we're changing that. And we'll do, let's pull this out. And we have the counter and definition. Okay, so now we just have the integer. Map folds upon map folds. And we need to flip this. So we don't care what the counter is, but we need to put the defs over here. Woo! All right. I am pondering whether we can turn this into use to make it a little bit easier to read, but I'm not positive because it's like callbacks, multiple callbacks. Convert to pipe, nope. There's no convert to use. We can do that transformation. Yeah, it is a dense map fold. Yeah. We can do the transformation ourselves by hand. So we can do this. Which be use accumulator D list map fold defs 0. The thing is, I don't know that it's worth. It is a little bit dense. What we could do is extract functions, perhaps. So maybe what we can do here is go extract this function. And we'll start with that one. Let's say uniqueify argument. And then we can say, so env is a dictionary, string to string. And the other bit that we have in this accumulator is the counter. Counter is an int. And argument is a and this is going to return yeah. Hello, welcome. What product you can do now? What? Can you explain what you can create now? What programming language is this one? This is, I'm using Gleam to write a compiler of a version of Racket. Gleam is, and you should have a look at the website. So this is some of the documentation. This is the package index. Oh, that's okay. So gleam.run is where you want to go. There's a nice little tour. So you can go try Gleam and it'll walk you through all the things. So you can see it looks a little bit like, it's got curly braces like some C-like languages. Use some keywords that look like Rust, but the semantics are more like Erlang with types, or Elixir. But one of the fun things is it compiles to JavaScript. So you can write things that run in the browser in Gleam, and you can also write things that run on the server, which I really like. So have a go look at that. We're gonna go back to this. I have made this complicated. So I think what I want to do is extract some functions here. Let's see if it'll let me do that. No. Let's just say unified definition. And this is going to take D, which is an L.definition, and env, right? And counter. And this, like the other things, is going to return an L.definition and an integer, which is counter. Okay, so I'm going to put a to-do in there. So I basically want to pull this stuff out and call it. So let's just pull this, and we'll swap these back. And then what we can do here is uniquify definition D and env and the accumulator. And this is where we do that pair dot swap again, like we did before. Okay. And this will be counter. Okay, so now we've flattened it a little bit. Yeah. Full stack website. I think you might be on the wrong stream. I appreciate your enthusiasm, but I think you might be on the wrong stream. I am not a designer. I am a coder. And I don't know how to help you, so I'm very sorry. Okay, so now I can possibly look at flattening this, because now we only have one list map fold in here. But it would still be basically use and then put the body in there, which is okay. I mean, I don't care for it as much. It's fine. You know, it's semantically the same, so yeah, we're gonna have problems with uniquify test. Okay. What kind of coder are you? Well, I do lots of things. I've done front-end stuff with TypeScript and JavaScript. I've done back-end with Java and Erlang and Elixir and Go and Node, and yeah, I'm old. In fact, in the last stream, someone called me Unk. And I've done a little bit of UI programming a long time ago. So I've done some C++, like command line stuff for university, but yeah. Yeah, I'm old. Oh yeah, and Python backend. Done plenty of that. Okay. Um, so getting back on track, so that we can finish up in a decent amount of time. What I want to do, ignoring the tests for now, I want to. Oh, it's gonna be. Yeah, it's gonna complain. And so I think what we're going to do is we're going to just comment out all those tests for now, because I want to make sure that we're going to comment everything. Okay. And we'll go back and fix the tests. Let's go back to, right. Okay. So let's take our thing from our example again from our parse test. And we're going to paste it here. And we're going to make sure shrink works. Okay. Now we're going to go to uniqueify. And the main thing that I'm looking for here is that this argument gets a new new name. This argument gets a new name. And then the references to those arguments get updated in the body. And the same thing will happen in Inc. So we got f.1, v.2. That's good. Those references got updated here. And then the argument here, x.3, got updated to be x.3. When did I start my coding? I started using BASIC in the early 90s as a teenager. That tells you how old I am, roughly. And then I went to university, started in 1997, and learned, Java and C++ and all that there. And that's how long I've been coding. So it's my coding inspiration. Oh gosh, that's hard. I haven't thought deeply about that. I have lots of inspiration on that. Okay, so this is good. This looks good. Note our main function also got the same. Well, but it doesn't have any variables. It doesn't have any lets in it. So interesting. But our map function has arguments that get renamed. Cool. Let's make sure that on a simpler program, let's use something, right, like let's use this and make sure that it still works. We got problems. What did I do wrong? I'm missing a paren at the end. I'm missing lots of parens. Okay, so the main thing about uniqueify is making sure that variables shadow. So when we introduce a new variable, it will shadow any variable that was in the outer scope. And I think this is related to your question from earlier, null ref pointer, in that maybe that was related to Gleam and not our language. But here, this uniqueify pass is, keeping track of which variables are declared. And giving you unique suffixes. So this one is x.1. And then when you go into this expression, you get x.2 declared. And so you return 10, and then you return, 10 plus 32, 42 is the answer to all of these. Okay. And I got 20. Why did I get 20? Okay. Interesting. How did it get 20? There's a bug. There's got to be a bug in our interpreter. All right. Well, at least we know this compilation is working there. Yeah, we're going to need to find that bug in our interpreter eventually. Okay, so we've updated Uniquify. We still have not started this reveal functions. But essentially it's going to probably build up a dictionary of all the names and arities. And then it's going to find all the places where those functions, because Uniquify made sure that local variables are renamed. It's going to find all the places where those functions are referenced and turn them into this funref structure. Okay, so no local variable, right? Okay, so let us very briefly fix these tests. We don't need to import the unit here. Okay, so we need to change this to this. So we're gonna have to change, not everywhere, program, open paren. Let's change it to program defs. And then we will fix all the places where it's wrong. Okay. So bear in mind, this is the import definition. And I think that we can copy that bit from, where's our shrink test? Where we did main. Yeah, definition main integer t. Yeah. And let's import integer t. Let's see, what do I have going on wrong here? Okay, so x1 is 32. This is just the example that we tried. So that closes that, the let, and that closes definition, and then we close the bracket, and then we close program defs. Okay. That was kind of a painful transformation. Okay, so we can paste that back in here. We're getting there. And my apologies for this being like not really thrilling content. I'm aware. But this is the sort of thing you have to do if you want to maintain something over the long haul. There's just no way around it. Okay, we're getting there. pretty sure that's getting to be mechanical. Okay, so let's run those tests real quick. Yeah. Okay. Cool. So we've at least verified that the existing stuff still works. I think what I want to do is make a Uniquify, let's say preserves function names test. Okay, so and rather than let's make a really simple program. So we're going to say program defs, and it's going to have a definition, fill labels. So the names are, we're going to have f, its arguments are a, integer t. Its return type is integer t, and its body is going to be prim plus var a integer 1. Okay, so really dumb. And then we're going to say we're going to have a main. So this will be our entry point for our program. It has empty arguments. It always returns integer t. Its return type. And its body is going to be apply var f, and then the arguments are going to be integer 41. Okay, so what I want to see here are so we're just copy this. Let p2 is this, and we're gonna see that this becomes a.1, and that this var here remains unchanged. Right? Okay, so we're gonna say assert Uniquify of p is p2. Let's run that test. Okay, and that passed. So as I would expect, given what we wrote in the code. So good deal. Since this refers to a top-level function, then yeah. Okay, what are we going to do? We are going to now, let's make a brief commit. Right, so we're going to update Uniquify pass for functions. Okay. And now we can go to reveal functions. The nice thing here is that we can take, basically, we're going to have to do our pretty printing as well. But we can basically take all these types. We're not going to do interpreting. So we don't have to worry about that. We just need to worry about pretty printing. So let's make our new language. Fun ref is what they're calling it. Oh, rename. Fun ref, right? And we can take we're going to take all of this, and then we'll eliminate the stuff that we don't need. We're going to write our own program type that's different. Okay, so we don't need type error because we don't, but we do need. I think that what we'll do is we'll import the types from. The main thing is we're going to change the expression type to have a permanent thing, which is funref name string arity integer, right? Yep, all that stays. So the thing is, their types don't need to change. So we're going to say import UC langs l fun type, and then we can get rid of this. And I don't, yeah. Why not? Type. Yeah, it's not a constructor. Okay. Okay, so now we have funref in our thing. Let us get. Let's go down here and find the pretty printing, because what we need to be able to do is, yep, format program. And I'm just going to copy that out. And our program is just going to be defs is a list of definition. So we can, yeah, we don't need to do that. We can import format type because we're not redefining it. Honestly, we could import the comp type. Basically, anything that is unchanged, we could import from the other thing. I want to look real briefly at what we did in some of the others. Yeah, I imported it through. So let's type comparison. We have to define our own primop though, because this is not, we haven't gotten to remove complex expressions yet, so you can have expressions in the primitive operator that are complex. Let's go down here. Okay, so we're just going to do p.defs, and we're just going to take this list map format def. Okay. So this is just our pretty printer. We don't need to be like horribly concerned with it, as long as we're okay with the other things. The main thing here is we need to add funref, and we're going to ignore the arity, and we're just going to say doc from string name. That's enough to be able to pretty print this sublanguage. Let's import format comp as well. Format comp. We're going to reuse that stuff. Okay. So now we've got lfunref. The other thing that I'm tempted to do when formatting that is to use the slash to indicate the arity. But that's not part of the that's an Erlang Elixir thing. That's not part of the Racket syntax. So I'm not going to do that. Okay, so what we're going to do is we're going to start reveal functions. Okay, so I need to import lfun. L. lfunref. Sorry. Let's call L in and L out. Reveal functions. And this is going to take an L in program, and it's going to produce an L out program. Okay. So we're going to have some very very kind of tedious transformations. Every time we convert from one intermediate language to another, we basically have to translate all the concepts there, right? So this is not let's just call it program. Okay, so what we're going to do is we're going to do let assert Okay, and then we are going to let's make a list of all the functions kind of as the environment. So we're going to do defs and we're going to do dict from list. Okay, so what we want to do here is get get the initial environment. That's what this is. We want def.name to point to funref of def.name and list length of def.arguments. Okay. I'm not positive, but I'm guessing, it doesn't make sense that it would do that. I mean, the arity is important for the call site. Maybe that's just what it is. I was about to say, does it allow you to define a name that has multiple arities? And I don't think that it does. Okay, so we've got the env. It's a list of string to expression. Now we need to process each definition. So let's just do this. Reveal definition. And we're going to do map over defs, and we'll take the env. So, and then our ultimate is to do that. Or we can pipe it. So we can say defs, pipe it to list map of that. And since constructors are functions, basically we can do that. Okay, so we need to do generate that function. And our first order of business is to extend the environment with all of the arguments of this definition. So and makes me wonder if we did anything in here that, no, okay. So can you fill labels for me? Okay. Ultimately, we want to return lout.definition. The name stays the same. The arguments stay the same. Return type stays the same. And the body is updated. So let body is to do. This is the form of our thing that we want to do our transformation on. Okay, and then we're going to have, since body is an expression, let's shoot, come on. Reveal functions expression. And we're going to modify our env here, but we're going to basically pass the body and the env. So let's go ahead and generate this function as well. Thank you, LSP. You're very, very helpful. And then what we'll do in here is just case. So this is going to be body. Let's call it expr. And just add all the patterns. And then we can go through and do the recursion as necessary there. Okay, so the first thing that we have to do is make sure that all of these arguments get added as variables. So we're going to say dict insert into env arg.0 lout.var arg.0, right? So it's saying when you go to look up this thing that is a variable, what are you going to replace it with? We need to make sure that because what we did up here is said, hey, this name at the global level is a function reference, and we want to make sure that all the arguments are there. And then essentially we are going to fill in all these clauses here based on the env. And we want to make sure that when we create new bindings that we propagate that into sub-expressions, right? Okay, so this is going to be pretty straightforward. This is int value, right? This is bool value. The op, we need to make a new reveal functions prim op. Okay, and then we'll go lout.prim. Okay, so this is the key one, that and this. Okay. So I think this is just lin dot or lout dot if, right? And this is reveal functions expr on condition E and B, and we'll do the same for if true and if false. Right, because these don't introduce any new variables. And this becomes lout.setBang var, and then reveal functions expression on value E and B. Yeah, I mean, this is fairly mechanical, so not interesting, but we have a lot of this code. Like, and actually, my opinion is it's actually a good thing that it's not, that it's very mechanical, because it does mean that you should be able to check it pretty quickly about is it correct or not. If you this has type is like a semantic annotation, by the way. So that we can expose allocations later. Value E and B and T, and then reveal functions. I want to get these mechanical ones out of the way before we do the interesting ones. And then this is list map arguments reveal function expression. Okay. So and we need to generate this function, and then let's just wrap it because that's what we're doing in the other clauses, just to be clear. Okay, so for var, when we get a variable, we need to check, and I'm going to put, maybe we'll just do case. what's wrong with that? It doesn't like that. Why not? Okay, well, let's do let assert. Okay. I had, where was it? In one of these other places, there's a like a env get or something. It's like in the interpreter. It's like, oh, get var is what it was. Yeah, so open, please. Okay, so it's like, yeah. Referenced unknown variable. Okay, so yeah, we'll just do that. Okay, so what we're doing here is we will have either defined it as a function reference at the top level, or we define it as an argument so far, and then the last bit is we just have to handle let bindings, and then we're done. So what we will do is say let binding is reveal functions expression on the binding expression. And the env. And then we're going to say expr is going to be also reveal functions expression on the expr, but we're going to insert into the environment var as var of var, lout.var. And that way, binding expression. That way we've got my dedication. Keep it good. Thank you. You're not an ugh. Oh, I don't know about that. Pretty damn old. I appreciate it. Thank you for coming to the stream and sitting through all this. Just to be consistent with the other ones, I think I'm going to inline that variable instead of doing it separately. And then we can get rid of the brackets there. Okay, so what did we do? We said when there's a let expression, which is just a single variable to a binding another expression to that variable, we now have this variable defined in the scope of this expression, so we have to insert it into the environment. That's basically all we're doing there. And then I think we just need to do this case op and fill all that out. This is going to be really straightforward. Value is an expression, so we need to do allow.negate. Again, these don't introduce any new variables. We just need to translate from one data structure into another. So again, this is going to be a little bit mechanical and annoying, but my editor's helping me out a lot right now. Do y'all hear that squeaky sound? How to learn a new tech stack, sir. Try really hard. That's not what you wanted to hear, was it? honestly, take what you learned from your first thing that you like, inspect what you learned from your first tech stack, right? Use those skills to apply to the new thing. I get a little bit frustrated with that kind of question because it's essentially, how do I learn? And I'm not really the person to answer that. You should perhaps consider looking at how you learned something to begin with. That's the best I can do. Yeah. And no, it's fine. I'm not offended. I want to be clear. I'm not offended. I just want to be honest in the fact that, you know, I'm talking through my process so you can maybe learn through how I think about things, but that's not necessarily going to be the way that you will be able to learn about something that you want to learn about. Okay. So we're almost there, folks, I promise. And then we'll be able to test this particular bit, I hope. And then we can call it a day because I'm running out of steam, if that were not obvious already. Old person and all of that. Index is an expression as well. Okay. Index v. Okay. So I don't know what to take away from this except that, you know, this feels a lot like the other passes that we've written. We don't have a way in Gleam to say, do, you know, just keep all of these things the same but tweak these variants. We have to have total coverage, and that's why this code is a little bit a mess. A mess is not the right word. It's a little bit like we're not highlighting the things that are important, that are different. But it's these two clauses that are different. Everything else is just sort of a pass-through translation. And then there's the preparation of filling the environment with the references to the top level functions. Yeah. I like to be a happy guy. And you know, thank you for that. I do enjoy doing this stream, even if it's not that often watched by folks. I do enjoy doing it. It brings me joy. So thank you for that. Okay, so we got reveal functions. I think that what I'd like to do, I'm going to go back here and I'm going to change this. So rather than just printing the name, I think I'm going to do something I said I wasn't going to do earlier. Let me pull this out. import Gleam int. Okay, so what that will allow us to do is go into our little explorer thingy, and we're going to introduce reveal functions, right? Oh, I need to put it in here. Yeah, so it comes after uniqueify. We'll put it right here as a variant of our pass. And then down here, we need to fill in all the other bits. Reveal functions, string to pass. We need to put it in here. Reveal functions is reveal functions. We're just making this happen. Okay. So now, after uniqueify, we can go reveal functions and do a lot of this. And then we're gonna put EOC langs L funref as LFR import. Where are we? Okay, and then we'll do LFR dot format program, and then doc to string 80. I should really extract that out as a constant, but okay. So we should have now in our UI, we have reveal functions. So let's use our example that we've been using. Reveal functions. Okay, where's our parse test? And okay, so note that it has this inc/1 and map to. That's probably not the best way to do it. Let's remove the parens from that. I think it's gonna let me put that in the paste buffer. It's going to remove our inputs. Let's just do that rather than putting the parens there. Yep. Okay, so looking here, it's saying call map to pass inc1 as the first argument. Note that hierarchy there. Map takes 2 arguments. It has a function from integer to integer, and the second bit is a vector containing, so a tuple basically, containing an integer and an integer. And you know, this just validates that that's the correct type there, and that this expression returns that type based on the type of map. So that has type is really just our type annotations on the AST. And yeah. So what we did was those places where it was found that a local variable, or you know, is actually referenced to a global function, we replaced it with that funref. That's what that's showing us. So I think that we did good today. And we can come back next week and add some tests for this pass. Or we could just take maybe about 10 minutes and do those. Why don't we just do 10 minutes? Reveal functions test. Okay. the deeper we get into the passes, the more I like to start from text, program text, and go all the way through the phases that lead up to that phase. So I think that we're going to do that. So we're going to say okay. No LFR. Okay. And then let's see here. Let's make, we'll call it prepared. And this is going to be l.program. And we've done this before in this stream. We're going to say parse.tokens string. Okay, so we're just making sure that it parses a program. And then we want to do l dot type check program. So we'll do let assert okay. Parse tokens input. I don't know why I did that. Okay, and then we will do p, and we're going to pass it to all the things that come before reveal functions. So let's get that. It's going to be shrink, uniquify, and I think that's it. Let's just call this program. Yeah, shrink, uniquify. And then we can pass, let's just make a reveal functions test and just make it really simple. And I think I want to use this example. Oops. Okay, so that's going to be our input program. And we're going to say P2 is reveal functions of P. And then what I want to do is look at the main function. P2 defs. Okay, so now we have the body of the main expression. And what I want to see is assert main is going to be Hey, explain about how to start coding without knowing anything about code. Let me finish this, and we'll address that question. Okay, give me just a moment. Let's see. So what we want is our expression here. I'm going to manually construct the syntax tree because it's actually not that big. LFR dot vector ref, right? And this is going to be int 1, right? So that's what our expression is going to be there. And then we have, this is going to be a has type, right? Because this expression returns a vector, so it's going to have has type around it. So we're going to need to fill in that, but let's go ahead and get the type in there. I'm sorry, this is lfr.hasType. That is going to be vector t, l dot integer t, and we're going to have this probably twice, so bear with me there. Okay, so our main function, all it's doing is, I'm going to construct this vector, I'm going to run some function on it, and then I'm going to pull an item out of it. That's what our main function is doing. Please explain, boss. Oh my goodness. Okay. How to start coding without knowing anything about code. Okay. So I'm going to relate maybe a little bit how I started learning to code. There are two things. One was when I started trying to learn to code, I did not have a computer. We had some computers at school, but they were very restricted in use. One of my friends, my classmates, his family had a computer. One of the units that we would do in my elementary school was there was a week or so, maybe 2 or 3 days, where we would, as part of learning geometry, we would go into the library, and they would have set up all of the computers, which at the time were Apple IIes. That's how old I am. That were set up to run Logo. So Logo is a very, very old language, but essentially it lets you draw turtle graphics. So it was about teaching you how to think about geometry in terms of angles and so forth. So we did stuff like if you want to draw a square, you would do like repeat 4, forward 50, right 90, right? So that would make your turtle go forward 50 units and then turn 90 degrees to the right, and then on the next iteration it would go forward 50 units and turn 90 degrees to the right, and forward 50 units and turn 90 degrees to the right, and forward 50 units and turn 90 degrees to the right. And that was pointing back at the original direction. So you circumscribed a square, and then you could generalize that to the other polygons that you wanted to draw. And of course, Logo let you change the colors. So we would do stuff like, have it flash a bunch of different colors as it was drawing stuff. And that was like really fun, and mostly fun because it annoyed the teachers, right? Okay. So after that, I mentioned my classmate had a computer. I think it was when I was in 6th grade. I was taking pre-algebra. Oh, thank you, Willie. Yes. This stream is more intermediate to advanced, yes. Thank you, Willie. That's very good. Yeah, you need to pick something small. You need to find the something that is simple enough for you to read and understand, but I think it's not just about learning the syntax. The key with coding is learning how to think about the problem. And I often take a top-down approach, which is to think about what is the overall goal I want to achieve, break that into pieces that I can achieve independently, or that maybe have some connection between them. And then I'll break down those individual pieces until I get down to the point where I can have like one line of code, right? Now, I don't always do that. I will sometimes be thinking about the entire space and the focus space at the same time, and the steps in between. And that's just a factor of I've done this for a very long time. But yes, and thank you again, Willie. Much love to you for coming to the stream and also helping out with our new folks. That is what that is sort of the approach that I go with. I'm sorry, and now I'm getting distracted. So I wish you all the best luck for that. This is not really the stream to answer that. I will do what I can. But this is not the best stream to do that. Okay. So I want to basically finish up translating this expression into our AST. So what I'm doing here is I want to make sure that this and this got turned into function references. So our apply expression takes the expression that is the function. In this case, we want to make sure it's a fun ref. Right? And the name is going to be map, and the arity is 2. Okay? And that's going to have a list of sub-expressions. And this is going to be, we're going to have a fun ref, which is, name is going to be ink, arity is going to be 1. We're just trying to validate that we did this transformation in the places where it's relevant. Okay. And then finally we have this, this has type again. Unfortunately, and we need this. It's just making sure we don't violate certain kinds of things. And we're creating a vector, and this is l.int 0 and l.int, no, not l, lfr, because I'm in the target language. Oh man, y'all got me distracted. 41. Okay, so what's the problem here? Oh, right. So I need to do prim. So constructing a vector is a primitive operation. Okay, so let's run this test. I thought this was going to take 10 minutes. It passed. Okay. So it took longer because we had a long explanation. But I feel pretty confident about that. So what are we validating here? We're saying that inside our program, references to functions that have definitions at the global scope get turned into this funref thing. And that's a good place to end it. So we're going to git add source and test. Okay. So this is, what chapter are we on? This is chapter 7.4. Is that what they called it? Reveal functions and the funref language. Okay. And that's a good, I'm going to push, that's a good place to end the stream. Thank you all for hanging out. And I don't want to discourage your, the basic questions. I'm happy to answer them. But please bear in mind that I'm focusing on a very particular thing here. Maybe we can do at a later date, Q&A stream or something. And I can talk more about how I got to this and maybe what you can do if you want to get started. So thank you all. Take care.